Hello Year 11. This is going to go through the mock paper 1 that you did for the triple chemistry. As I go through this, I'm going to try and highlight which topic the questions are assessing and how I got to the answers. It's more important that you understand where you gained or lost mark than it is in getting the exact answer for that question. In your actual exams, they will ask very similar questions with slightly different examples and numbers and so on. Getting to the right answer is more important than just memorising the particular answers for this paper. Question 1 part A was about topic 5 and the transition metals. Question 1A asked you about alloys of gold, but the same ideas would apply to any mixtures of metals or steels or other examples they might use. So 1A asked to explain why 18 karat gold is stronger than 24 karat gold, and they gave you a table with some information in. The key point here being that 24 karat gold is 100% gold, so it's a pure metal, whereas 18 karat gold is a mixture of gold and silver and copper. So the answer I should have said is that the 18 karat gold contains ions of different sizes. The mark scheme actually irritatingly talks about atoms rather than ions, but ions is the better phrase. Then, that is my statement of fact, that is a fact. However, the explanation is the more important part here, and the explanation is that the different sized ions or atoms prevent the layers of metal ions from sliding over each other. You were allowed to use a diagram for this question, and we could have done so. If you wanted to, the best thing to do would have been to draw both. We could have said 24 karat gold would contain very similar sized ions and we could have said that the 18 karat gold contained very different sized ions. Doesn't matter exactly which sizes you put in, but something like this. Question 1 part B asked you to find the purity of gold in carats using this graph. This doesn't actually require any chemistry, this is just maths, it's percentages and graphs. So, in the question, they said the mix has a mass of 5 grams and contains 2.9 grams of gold. First thing to do is to work out a percentage of gold to be able to work out the carats. So I should have done my 2.9 grams of gold divided by the 5 grams of the necklace, and that gives me a number of 0.58 multiplied by 100 to get a percentage gives me 58%. I should then have looked at my graph and said 58% is on this line here, so I should have read up my graph to this point and then read across here and got an answer approximately there. Depending on exactly where you read your line, you were allowed a number anywhere between 13.8 to 14.0. For question C, you were asked to calculate the number of gold atoms in the ring. Before I do anything here, if I just have a quick think, I know that atoms are really small, and therefore my answer should be a stupidly big number. I've been told that my gold ring contains 3.94 grams of gold, and I've been given the relative atomic mass and the Avogadro number. First thing I should do is to work out the number of moles of gold in this ring, which is equal to the mass divided by the relative mass, which is going to be 3.94 divided by 197, which gives me a number of 0.02 moles of gold. I know that 1 mole of anything contains the Avogadro number of particles or atoms or ions or whatever I'm talking about here, and therefore the number of gold atoms is just 0.02 multiplied by the Avogadro number, which is 6.02 times 10 to the 23, which should give me a final answer of 1.204 times 10 to the 22. Because they had not specified a particular number of significant figures or decimal places, it's fine to leave it like that. You would also have got the marks for 1.20 or 1.2 times 10 to the 22. Question 2 is about topic 5 and electrolysis. For question 2, part A, part 1, you've just been asked for the hydrogen test, which we should all know. The hydrogen test is you put a lit or burning splint into the gas or hydrogen, and if this is hydrogen, hydrogen will burn or catch fire or ignite with a squeaky pop noise. It's not good enough to just say squeaky pop test. You must talk about putting this lit or burning splint into the gas. Question A, part 2, is asked for the name of gas X that forms at the positive electrode. So if I look at my diagram, my positive electrode here, I have got sodium sulfate solution. So my positive electrode is going to attract negative ions. Therefore, I have not got chloride, bromide or iodide, and therefore the gas being produced must be oxygen. Part 3, state what is meant by the term electrolysis. Electrolysis, told you the answer in the question. Electrolysis means to break apart using electricity. So the written answer for the 2 marks needed to involve the word electricity. So using electricity or electrical energy or flow of charge, anything along those lines, but electricity is the best option. To break apart or decompose or split up. An electrolyte or compound or substance. You could have specified this is an ionic compound. That was good. You didn't have to for the mark. You could have said to separate ions, but that's less reliable. To get the marks, you needed to specify using electricity to break apart or split up a substance or a compound. Question B is asking about calculating a concentration in grams per decimeter cubed. and I've been given a mass in grams and a volume in centimetres cubed. Two ways of doing this, either way works. The first way is to say that my 250 centimetres cubed needs to be converted into decimetres by dividing by 1000, which gives me an answer of 0.25 decimetres cubed. I then need to take my 28.4 grams divided by my 0.25 decimetres cubed, and that will give me an answer of 113.6 grams per decimetre cubed. Alternatively, I could do my 28.4 grams divided by 250 centimetres cubed, and that will give me an answer of 0.1136 grams per centimetre cubed, and I can then multiply that by 1000 to get an answer of 113.6 grams per decimetre cubed. So it does not matter which way round you do the unit conversion, you still get to the final answer. However, I have been asked to give my answer to 3 significant figures, so my final answer should be 114 grams per decimetre cubed. Question C is just asking me to work out an ionic formula, which I should do using the crossover rule. They've given me the ions present, so I can just write out my ions. And then the sodium just has a positive charge, so I don't write any number after the sulfate, and that disappears. The sulfate has got a 2- charge, so I put a 2 down here. And therefore my final answer is Na2SO4. Question 3 is about topic 4 and the reactions of acids. For the first part, part A, part 1, you are asked to complete the balance equation. They've given you the word equation at the top, and you just needed to write in the formulas of copper sulfate and sulfuric acid. Copper sulfate, the copper ion is 2+, and the sulfate ion is 2-, because they have the same size charge. The 2+ and 2- cancel, and copper sulfate is CuSO4. Sulfuric acid, we should know, but if you forgot it, we can work it out. All acids contain hydrogen, and the hydrogen ion is H+. The sulfate ion is again SO4, 2-. Here the charges don't cancel. The positive charge on the hydrogen has no number, so we ignore that. But the 2- on the sulfate means I need 2 hydrogens to balance the charge, and therefore sulfuric acid is H2SO4. Just double checking this is balanced. I've got 2 hydrogens on the left and 2 hydrogens on the right, so they are the same. I've got 1 SO4 group on the left and an SO4 on the right, so they are the same. I've got 1 copper on both sides, 1 carbon on both sides. I've got 3 oxygens on the left, but on the right side I've got 2 oxygens here and 1 here, so they balance. For A part 2, you've been asked to calculate the relative formula mass of copper carbonate, which is just asking me how heavy is the formula mass of that substance. So I'll add up how heavy each individual element is and then add them together. So copper is 63.5, carbon is 12, oxygen is 16, but there were 3 oxygens in the formula, and therefore I need 3 oxygens in my mass. And if I add all of those together, I should get a final answer of 123.5. There is no rounding or significant figures here, so my final answer is 123.5. For question A part 3, the test to show a gas is carbon dioxide is we bubble the gas through lime water and the lime water turns cloudy. For part B, you are given a reaction between sulfuric acid and copper carbonate, and you are asked to show two observations, i.e. things that you would directly observe, things you can see or hear, but that would show the reaction has finished. And if the reaction has finished, that means nothing else new is happening. Lots of people wrote answers about you would see fizzing, or you would hear bubbles, or you might see a colour change, which is all things indicating that a reaction is happening. If the reaction has stopped, you would not see those happening. Things we might have seen is that the bubbling or fizzing has stopped. That is one indication the reaction has finished and is no longer occurring. We might see that a colour change stops, or there is no further colour change. Or we might say that solid copper carbonate remains in the solution. Or we could say that the copper carbonate stops dissolving. Okay, for question C, you are asked to draw a dot and cross diagram for a molecule of carbon dioxide. So this is actually topic 2, the bonding topic. You've been given the electron configurations and asked to show outer electrons only. So my carbon has got 4 outer shell electrons, and oxygen has got 6 outer shell electrons. The first thing I'm going to do is I'm going to draw in my outer shells of carbon in the middle and oxygens either side. And then this is a dot and cross diagram, so I'm going to represent my carbon's outer shell electrons with crosses and my oxygen's outer shell electrons with dots or circles. This is not complete because my carbon only has 6 electrons in its outer shell and my oxygen only has 7, and all 3 atoms need to have 8 electrons to fill their outer shell. So what I'm going to do is I'm going to move the unpaired electrons from the carbon and put those in the overlaps, and I'm going to move the unpaired electrons from the oxygens and put those in the overlaps as well. I now have a completed dot and cross diagram with all electrons paired up. My 2 oxygens have got 4 shared electrons and 4 of their own to make 8, and the carbon has got 8 shared electrons, so all of these atoms have a full outer shell. Question 4 is also about acid reactions, which is topic 4. The first part is they've given you the steps in a titration and asked you to put them in the correct order. They had already given you step 1 and step 5, and we just need to decide the rest of the steps. So step 1 is to fill the burette and record the initial reading from the burette. The next step is going to be to measure out your other solution that's going to go into the conical flask. So that must be step L, is step 2. Then, once I've measured out my potassium hydroxide, I need to pour that into the conical flask and add the indicator. So step J must be step 3. Then they've missed out the step of put the conical flask under the burette. So the next step is going to be to add the hydrochloric acid into the conical flask until the indicator changes colour. So step N is step 4. And then step 5, step M, is to take the final reading from the burette, which is the last one. So that all makes sense. So I should have step L, and then step J, and then step N. Question 2. Suggest an alternative piece of apparatus that could be used in step L. Step L suggested a measuring cylinder. So I cannot use a measuring cylinder because it says an alternative piece of apparatus. So the best one here is a pipette. Those are the ones that you should have used in the titration core practicals, the glass pipettes with the rubber sucky squeezy thing to fill them. You could also have used a burette because you could have filled a second burette up and used that to run the potassium hydroxide solution into the conical flask. You couldn't have anything else really. So the suggestions of beakers and so on, a beaker is nowhere near accurate enough to get exactly 25.0 centimetres cubed. For question B, you were asked about getting a pure sample of solid potassium chloride, and you are told a student has done a titration and then repeats the titration rather than using the original version. The reason for this is that the original titration mixture contains an indicator. That's how you know when the reaction is finished. And therefore, because that original titration mixture contains an indicator, you cannot get a pure salt, because pure means there's nothing else in this apart from potassium chloride. If there's an indicator in this, you've not got pure potassium chloride. So you would repeat the titration without an indicator to avoid contaminating the salt. Part 2, you are told that you've got an actual yield and a theoretical yield, and importantly, they've told you that this gave you a percentage yield greater than 100%. So this is a very rare situation. Percentage yields should be less than 100%. They told you in the question your answer should be more than 100%. So percentage yield is equal to the actual yield divided by the theoretical. We've been told the actual yield was 0.84 grams. The theoretical yield was 0.70 grams. And therefore, I should get an answer of 1.2. As a percentage yield, this needs to be converted into a percentage, so I should multiply by 100 to give an answer of 120%. Normally, if I got 120%, something has gone very wrong because I've made more product than I possibly could have. However, they told me in the question my answer should be more than 100%, so that is right for this question. For part 3, they asked you to give a reason why this actual yield was greater than the theoretical yield. If we think about what they did, in this experiment, they then evaporated off the water to be left with the solid potassium chloride. The reason why we appear to have made more product than is possible is because the potassium chloride was still wet. Or we could have said that not all of the water had been evaporated. Or any other words to those effect that meant that we hadn't just got potassium chloride, that there was still water inside that potassium chloride. Part 4 is asking to calculate the atom economy for the production of potassium chloride. Atom economy is essentially the efficiency of a reaction. It is the mass of the useful product divided by the total mass in the reaction. There are two ways of working this out. We can either do the mass of the useful product divided by the masses of all of the reactants, or we can do the mass of the useful product divided by the mass of all of the products. It does not matter which way round you do this, we get exactly the same answer for both. So if we take the left side first, potassium chloride, I've been given the relative masses in the question, is 74.5. Potassium hydroxide is 56. And hydrochloric acid is 36.5. And if I put this into a calculator, I get an answer of 74.5 divided by 92.5, which is 0.8054. If I take the other way of working this out, potassium chloride is still 74.5. So I get 74.5 divided by 74.5 plus 18, which gives me an answer of 74.5 divided by 92.5, which is still 0.8054. I've been asked to give my answer as a percentage, and therefore need to multiply this answer by 100, which gives me an answer of 80.54%. However, I've been asked to give my answer to one decimal place, and therefore the last mark is to give my answer as 80.5%. Question 5 is about the topic 3 content on separating mixtures. The first question has asked you to draw a labelled diagram of the apparatus used to filter the mixture of sodium chloride and some insoluble substances. If we are separating a mixture of a liquid and a solid, we're going to filter this. So we should have a diagram looking something like this, with a funnel and a filter paper and a conical flask. You got one mark for this diagram, and then the second mark was for adding the labels. So this thing should be a conical flask. This is a funnel, and this is a piece of filter paper. Several people lost marks for drawing the funnel incorrectly. The marks were for a correct diagram, and if your diagram had the funnel closed off at either end, you did not get the mark for the diagram. Part 2 asks how you could get a sample of pure, dry sodium chloride crystals from the filtrate, i.e. the liquid after you have filtered out the insoluble bits of rock. So the first thing I would say is that we would heat the solution or the filtrate to evaporate some or most of the water. Because we've been told that we've dissolved the rock salt in water, we need to get rid of some of this water. And important point here, we've been asked for crystals. If we'd just been asked for dry sodium chloride, this could be heated to dryness straight away. But to form crystals, the crystals need time to form in the liquid. So, to give these crystals time to form, once we've evaporated some of the water, the first mark, we then need to leave the solution in a warm place or an oven to evaporate the remaining water slowly. And lastly, to make sure the crystals we obtained are dry, we would then specify we would dry the crystals and there's several options here. We could dry the crystals on filter paper, or we could dry them in an oven. For question B, this is again about topic 3 and this is about chromatography. For part 1, you are asked to calculate the RF value of the dye that is present in both inks X and Z. So I would look at inks X and Z on the chromatogram. Ink X is here and ink Z is here. The only dye that is in both of these is this dye here. So I would calculate the RF of that dye. My RF value is found by finding the distance the spot has moved and dividing by the distance the solvent moved. The spot, if you look across carefully, measuring from the middle of this dot, is at around about 3.9. The solvent came across at approximately 6.5. Doing this should give me an answer of 0.6, and therefore my answer is 0.6. For part 2, you were asked to state what could be changed in the experiment to make the RF value more accurate. This was a really quite difficult question. It's a common question but not normally asked about chromatography. If you are asked to give a change to an experiment, you have to specify an actual change to the equipment used or what they did. Just saying they should use a ruler with smaller divisions between the units would make your answer possibly more precise but not more accurate. What we should have said is either use a longer piece of paper or you could have said use a different type of paper. Both of those would have worked because they might, with a longer piece of paper, the dots would have to travel further, as with the solvent, and therefore you are more likely to get a better value closer to the true value. Using a different piece of paper, the dots may have moved more or less and therefore may also have given you a value closer to the true value. In part 3, you were asked what would you need to do to separate the dyes in ink sample Y, which did not move from the start line. If the dyes were not moving, they were not soluble in the solvent. So we should have said what you would do is a change to the experiment, i.e. a change to the equipment or the chemicals, and explain why. So we should have said we would use a different solvent. That is the change to your experiment. And we should use a different solvent which dissolves ink Y, or which ink Y is soluble in. And then we could have said because ink Y is not soluble in the first solvent. Question 6 looks like it's about transition metals, which is topic 5, but the first question is actually about isotopes, which is the very first topic back from year 9. So to calculate the relative atomic mass, we need to find the average of the masses of all of these isotopes. So what I should do, reading the graph, I should work out the value of each isotope. So this first one is 8. This second one, this bar is halfway down to the next one, so this is 7. This one, this line here would be 74, so this is 75. This one is 6, and this one is 4. Then I need to multiply the abundance of each isotope by their mass. So I need to do 8 times 46 plus 7 times 47 plus 75 times 48 plus 6 times 49 plus 4 times 50. And if you put that into a calculator, that gives me an answer of 4,791. That has got me the first mark. However, I should be able to see from this that my final answer must be somewhere between 46 and 50, because those are the heaviest and lightest isotopes, and therefore the average must be somewhere between them. And the isotope 48 is by far the most common, so my answer should be roughly 48. And what I need to do here is remember that this does not take into account that I'm working with percentages. So I then need to divide this answer by 100 to get my answer of 47.91. And I have not been asked to give any number of significant figures or decimal places, so therefore my final answer is 47.91, which is approximately 48, which makes sense. Question B, the reaction with oxygen is an oxidation reaction. This can't be any of the others. Crystallation and distillation are methods of separating a mixture, and neutralization is when an acid reacts with a base. Part 2, you have been asked to use this equipment to describe how you could find the mass of oxygen that combines with a known value of iron wool in a crucible and lid of known mass. So what that means is that if you know the mass of the crucible and lid and iron, how could you work out the mass of oxygen that has reacted here? This is an experiment that you should have done before. The mistake a lot of people made was to think we're trying to keep oxygen out, but we're not. We're trying to get oxygen into this crucible, and to do that, the first thing to do is to heat the crucible, because if we don't, the reaction will be much, much, much too slow. And we need to open the lid a small amount to let oxygen in. If we don't open the lid, all the oxygen inside will react with the iron, and therefore there will be iron left that has no oxygen to react with. We need to let oxygen in to allow all of the iron to react. You could specify here the reason why we only open the lid a small amount is to prevent the iron oxide from escaping. That's not such an issue with iron oxide, but is very true of the magnesium oxide you probably did in this reaction. Other points we should then say. We need to find the mass or weigh the crucible lid and iron oxide. We then need to take this final mass away from the mass of everything we started with to find the mass of oxygen. So we should say the mass of oxygen that reacted is going to be equal to the final mass of product, crucible and lid, minus the start mass of the crucible, lid and iron wool. Because the difference in what you started with and what you ended with is the mass of oxygen that reacted with the iron wool. There was a fourth possible point we could have said, which is that we should keep heating until the mass does not change, or total mass. Does not change. The reason for that is that if the mass is still changing, then the reaction has not finished. Really, you should do this and find the mass or weigh the crucible in iron oxide, and then you should reheat this, and if the mass is still changing, you should keep reheating the crucible until the mass doesn't change anymore. Although that fourth point wasn't necessary to get all 3 marks. Question C. You have been told you've got a certain mass of iron reacting with a certain mass of oxygen to form an oxide of iron. You have been asked to determine the formula of this oxide of iron and use it to complete the balanced equation. The word "it" there is really quite annoying, but I can't beat the exam board for using it. So, the first part. If we've been asked to determine the formula of a compound, this is an empirical formula question. And therefore, we need to find the simplest ratio of atoms, or the simplest ratio of elements, or the simplest ratio of moles. And the easiest way to do this is to lay out our working out as a table. So I've got my masses in the question. I've got the relative atomic masses, either from a periodic table, or in this case they've given this to me in the question. I then need to work out the mass divided by the relative atomic mass, and finally a ratio. The masses I was given the question. I've got iron and I've got oxygen. I have 2.24 grams of iron and 0.96 grams of oxygen. And my relative masses are 56 for iron and 16 for oxygen. Lots of people put these numbers in the wrong way around. You must always do the mass divided by the relative mass. Doing it the other way around doesn't make any sense. So this should give me an answer with 2.24 divided by 56 should be 0.04, and 0.96 divided by 16 should be 0.06. So that is my ratio of iron to oxygen. I should then simplify this to the smallest whole number ratio I can. The easiest way of doing that is to divide both sides by the smaller number in the ratio. Which gives me an answer of 1 to 1.5. I cannot have 0.5 in a formula, and therefore I should double everything to get a final ratio of 2 to 3. Lots of people got to this stage and then forgot that we have been asked to write a chemical formula. You've not been asked for a ratio, you have been asked for a formula. And therefore, I've got 2 ions, so it is Fe2, and 3 oxygens, so O3. My first mark was for doing my division, the second mark was for my ratio, the third mark is for that formula. For the last part, balancing this, I should have written in the formula I have just found, and then I should balance this. If I do the oxygens first, I have got more oxygens on the right, so I need more oxygens on the left. I now have 4 oxygens on the left, so I need more on the right. I now have 6 oxygens on the right, so I need to change that 2 for a 3. I now have 6 oxygens on the left, 6 on the right, those are balanced. And finally, I have 2 times 2 is 4 ions on the right, so I need 4 ions on the left. Question 7 is all about the topic 6 content of equilibria. So question A part 1 has asked you to explain the effect of increasing the temperature on the yield of the products. And there's a couple of points here. First off, they've asked about stage 1, and therefore I'm only interested in this equation here. Second, they've asked about the yield of the products, and lots of people lost a mark for just talking about the yield. And in a reversible reaction, we might be asking about the yield of the reactants. You must talk about what they've given you in the questions. So, the effect of increasing temperature on the yield of the products. They have told us that stage 1 is endothermic, and therefore, if I increase the temperature, the system will try and reverse that process by doing the endothermic reaction. So increasing temperature means there will be an increased yield of products. Which has happened because the equilibrium it's explained because the equilibrium has moved to the right, and that's really all you had to say for that, but it would be better to say the equilibrium has moved to the right as the system favours the endothermic reaction. Right, part 2 has given us an overall equation and has asked us to calculate the maximum volume of hydrogen in decimeters cubed measured at standard temperature and pressure that could be made in this reaction. And we've been given a mass of methane. This is one of the reacting mass or mole calculations. What we need to do first off is to convert from a mass of methane. We then need to work that into moles of methane. We can then use the equation to work out the moles of hydrogen, and we finally convert that into a volume of hydrogen. And with any of these calculations where it's not a simple one-step thing, it is always worth planning out in advance what you're going to do before you stick numbers in. So, first off, my moles of methane, moles, when I'm working with masses, is going to be equal to the mass divided by the relative mass. So I'm going to have 0.40 grams divided by the relative mass, which is 16, which means I have got 0.025 moles of methane. First mark. Then I need to work out my moles of hydrogen. In my equation, 1 molecule of methane becomes 4 molecules of hydrogen, and therefore 1 mole of methane becomes 4 moles of hydrogen, and therefore my moles of hydrogen is simply going to be my moles of methane multiplied by 4, because these are in a 1:4 ratio. Whatever value my methane is, my hydrogen is 4 times that. So it's going to be 0.025 multiplied by 4, which means I have got 0.1 moles of hydrogen. Lastly, they told me in the question that 1 mole of any gas occupies 24 decimeters cubed, what's called the ideal gas constant, and therefore my volume of hydrogen is my number of moles multiplied by 24, which means my final answer is 2.4. And that is in decimeters cubed, because they told me 1 mole occupies 24 decimeters cubed. So I don't need to do any unit conversions. There's nothing on here about decimal places or significant figures. So my final answer is 2.4 decimeters cubed. Question B is the first 6-mark question in this paper, and it's probably the worst answered question in the whole paper for most people. Lots of people didn't really understand what they were being asked to do and completely missed the fact that this is in a spacecraft. And therefore, you can't make points about better for the environment or less polluting or nasty to the animals or destroys habitats or anything else because it's in a spacecraft. Too many of you are still trying to answer these questions as if they're geography questions and talk about generic pollutants and bad for environment or eco-friendly. It's rubbish. Please don't write that sort of stuff in a chemistry exam. The points we should have got. Everyone should have got at least 2 marks from this. If we go through this, but before we do, a quick note on the command word. This question said evaluate, and evaluate is a really rare question type for chemistry. I've not seen more than 2 of these in the new exam spec. However, evaluate is not the same as compare. Compare means what are the advantages, what are the disadvantages. Evaluate means they want you to list some advantages, and you don't need a huge list. 2 or 3 is fine. And some disadvantages. And a conclusion. So many people completely missed out the fact that if at the end they'd written, in conclusion, I think fuel cells are better, or I think chemical cells are better because, and they would have got a mark just for that. Second point, almost all of you completely misunderstood what a chemical cell is. And I know it's only a tiny part of one lesson and we didn't do it in much detail, but a chemical cell, we should know from physics, is what most of you refer to as a battery. If you take an ordinary AA type battery and cut it in half, you've got 2 chemicals in there, 1 chemical on the inside, 1 on the outside. When they react, electrons move between them because all chemical reactions are the movement of electrons, and electrons flow from one terminal round to the other, which is what causes an electric current. When you don't plug a battery in, the chemicals can't react, nothing happens. It may well be that you quickly pause this video and quickly think, actually, now, knowing what the word evaluate means, and knowing that chemical cells are batteries, and I've been given the equation for what happens in a fuel cell, you could quickly stop and write in a couple of points you now think would get you more marks. I suspect most of you, with that hint, could probably add another 2 or 3 marks onto what you've got. With that said, the kind of things we could have put, and you did not need to write all of these, you really didn't, providing you had some advantages and some disadvantages and a conclusion, you could have got all 6 marks with really only about 6 or 7 bullet points in total, including the conclusion. Okay then, what we should have said. First off, advantages of a fuel cell over a chemical cell or batteries. First thing, the fuel cell only produces water. You were given the equation, the only product is water, which means for a fuel cell, lots of people started talking about this as if it was a diesel generator and we're burning petrol. We're not. They gave you the equation there. The only product is water. So that's 1 mark already just for that. The second mark is in a spacecraft, water is really quite handy. So the second thing we could have said is the water produced can be drunk by the astronauts. That in itself is a major advantage of a hydrogen fuel cell. You don't need to take water with you separately packed into your spacecraft. Water's heavy and therefore requires more fuel to lift off the ground, and the spacecraft has to be bigger, and so on and so on and so on. If you can make water while you're there at the same time you're making electricity to keep your spacecraft running, that's awesome. Other things we could have said in comparing to chemical cells. A fuel cell does not run out. Providing there is fuel. This point, hydrogen is rocket fuel. You're going to need it anyway. Oxygen, you need to burn the hydrogen and for the astronauts to breathe, and therefore you're going to have loads of them. The fuel cell does not run out, unlike a chemical cell. Chemical cells, batteries, once the chemicals have been used up, if it's a non-rechargeable battery, you'd normally throw it away, but you can't do that in a spacecraft because you're in space. If it's a rechargeable battery, you've got to put the same amount of energy back in the form of electric current to recharge the battery. This is why chemical cells in a spacecraft are not a good idea, because if you're relying on them to generate all of your electricity, you've got to bring enough batteries for the whole trip. So another advantage of a fuel cell, what we've just said, is that used chemical cells take up space in the spacecraft. And the fuel cell does not run out. In a similar point, we could say that spare chemical cells need to be brought along, which increases the mass of the spacecraft and therefore requires more power and therefore more fuel, which requires an increase in mass because the fuel has mass, and therefore you need more fuel to lift that fuel, and it's all the same idea. In a spacecraft, you want the spacecraft mass to be as small as possible, so it requires the least energy to lift off and reach space, and if you can do that using a constantly renewed fuel cell rather than lots of batteries, that is the way to go. Other things we could say. The voltage produced by a fuel cell is constant, but chemical cells experience what's commonly referred to as voltage drop, but chemical cells decrease in voltage, because voltage is a potential difference. It is the difference in potential between your reactants, and as your reactants start to react, there is less reactants available, and therefore a lower potential, and therefore a lower voltage is produced. However, chemical cells decrease in voltage as reactants or chemicals are used up. If you wanted to, you could have done a little graph for that. If we were plotting time and voltage, a fuel cell will look like this, and a chemical cell will look like that. That is absolutely not necessary, but just in case you're not quite understanding the idea. A fuel cell, providing you keep supplying hydrogen and oxygen, they will react at the same rate and therefore generate the same voltage, which is really useful. A chemical cell, a battery, supplies the same voltage for most of the time, but as the chemicals begin to be used up, the voltage starts to decrease, and eventually the chemical cell runs out of reactants and stops working. Those are the main advantages. And honestly, that's 1, 2, 3, 4, 5, 6 points. You only really needed 2 or 3. If you got the ones about the water being the only product that can then be drunk by the astronauts, that's probably enough for an advantage to get the 6 marks. Okay then, disadvantages of the fuel cell. What we could have said. First off, hydrogen is flammable. So we could have put in that hydrogen is flammable or explosive in the right conditions, and therefore could be dangerous. Or cause a fire. Personally, I think that's a bit of a rubbish point, because a spaceship is essentially a massive hydrogen tank that floats about and you occasionally burn a small amount of it. However, it's a point that is valid. Other disadvantages is that hydrogen and oxygen are both gases, and are therefore difficult to store, because the gases need to be compressed, which requires energy. They also need to be trapped. Hydrogen in particular is a very, very small molecule and tends to escape gradually over time. It might be like helium out of a balloon. So we should put here hydrogen can escape through tanks. Again, really a bit of a rubbish point, because a spaceship has got massive tons of these, but it is a point that you could make. Other points we could say is that fuel cells have a limited output voltage. What that means is that if you are relying on 1 or 2 fuel cells to provide the energy for your spacecraft, there's a maximum amount of electricity they can supply per second, and therefore it doesn't matter how much you might need in an emergency. If you've got a certain size fuel cell, you've only ever got a certain size voltage available. If you are using lots of chemical cells or batteries, you can simply plug more batteries into a circuit to increase the voltage. A fuel cell, what you've got is what you've got, and that's it. The other point we could have said is that fuel cells are much more expensive than chemical cells. And again, it's not really a good point, because if you're launching a spacecraft, it's going to be costing you millions, if not billions, to launch the spacecraft anyway, and therefore spending a tiny percentage of that on getting some decent fuel cells is money well spent. However, it's another point that is in the MARC scheme and is a fair. And another point we could say is that fuel cells require a constant supply of hydrogen and oxygen. And that really is probably the main disadvantage of fuel cells. If you have got a stack of batteries, it doesn't matter unless you start freezing them or poking holes in them. Those batteries will have got a particular voltage in them that you can reliably get out in almost any situation. If you've got a fuel cell, it works providing you have your supply of hydrogen and oxygen. As soon as you lose either the hydrogen or oxygen supply, the fuel cell stops working straight away. It's not like if you've got a stack of batteries and suddenly everything breaks on your spaceship and you can just keep manually plugging in new batteries each time the old one runs out. If the power fails and you cannot get hydrogen and oxygen to your fuel cell, you've got no electricity and therefore can't restart anything. So, lastly, the conclusion. And it doesn't matter which way you went with this, either side is acceptable, providing you gave a valid reason. So I think most people would say a fuel cell is better than chemical cells. In a spaceship. Not everywhere. If your phone ran on a fuel cell, it would be really, really inconvenient because you have to keep plugging it into a hydrogen and oxygen supply every time you wanted to use it. But in a spaceship where you are cut off from any resupply or anything else and all you've got is what you've got with you, a fuel cell is probably the best option. So, in a spaceship, because, and here you just had to restate a couple of points from earlier and say that you think they outweigh the disadvantages. So because drinking water is produced and no used cells need to be stored. Which outweighs the risk of fire. Or, we could go the other way, we could have said chemical cells. Are better than fuel cells in a spaceship because, and going back up here, hydrogen is flammable and a fuel cell could set the ship on fire. Which outweighs having to replace used chemical cells. Either one of those conclusions would have been fine, providing that you were referring to advantages or disadvantages that you wrote in your answer. Question 8 is mostly about topic 1, about atomic structure, but also involves some stuff from topic 7 as well. So, first one, calcium has an atomic number of 20 and a mass number of 40. We should remember that the number of neutrons is equal to the mass number minus the atomic number. So, atomic number is 20, therefore 20 protons, so therefore must be either A or C. And then the number of neutrons, 40 minus 20 is 20, so my answer must be A. Part 2 is about the periodic table structure. You were asked here for which period calcium is found in. Lots of people wrote stuff about calcium being in group 2 because it has 2 electrons in the outer shell. That is totally correct, but also not relevant. You were asked for which period calcium can be found in. The periods are the rows going across. Every new period has got another electron shell. Calcium has got 1, 2, 3, 4 electron shells, and therefore calcium is found in period 4. Because, this is an explain question, because calcium has 4 shells of electrons. Part B. One similarity in the products of the reactions of calcium and potassium with water. And they have told me that hydrogen gas is produced. I cannot say there are bubbles or fizzing or effervescence because those are observations, they are not products. A product is a chemical. I can't say hydrogen is made because I've been asked for one other similarity and they've already told me hydrogen is produced. And therefore, I should have said that both produce or make a metal hydroxide. Or you could have said potassium makes potassium hydroxide and calcium makes calcium hydroxide. Either one is fine. And part 2, you are asked to explain why potassium is higher in the reactivity series and reacts more vigorously with water than calcium. So why potassium is more reactive than calcium. Lots of people wrote really good stuff on this that didn't really address the question, and this was quite a difficult one to get right because the answer was so simple. We just need to say that potassium loses electrons more easily than calcium. Lots of people wrote excellent stuff about how potassium's outer shell electron was further from the nucleus than calcium's, and therefore there was a less strong attraction between the opposite charges, which is fantastic. But for a 1 mark answer, all you had to say was potassium loses electrons more easily. However, there had to be some sort of comparison there. Just writing potassium loses electrons easily did not get you the mark. It's potassium loses electrons more easily than calcium. You must have that comparison. You've been asked why potassium is more reactive than calcium, so you must explain potassium loses electrons more easily than calcium. Question C is another long answer question. You are asked to explain in terms of bonding and structure why the properties of calcium chloride are different from the properties of reactants calcium and chlorine. Lots of people just completely ignored the things about bonding and structure and started talking about how calcium chloride is the average of calcium and chlorine. No. You've got to talk about bonding and structure. And we should remember there are three main types of bonding. There is ionic, there is covalent, and there is metallic. We should have said the calcium chloride is ionic because it is made of oppositely charged ions that attract together. The chlorine is covalent because this is non-metals joined together. And calcium is metallic because this is a metal. And if you got that point, most people who got to that stage then got most of the marks. If you didn't get that bit of the question, chances are you didn't get many at all. This is topic 2. It's the stuff we did right at the start of year 10. And it's an area where it's really easy to get lots of marks or lose a lot if you don't spot what the question's asking you to do. The other thing that was an issue was lots of people have clearly learnt some of the key words and are determined to write them in even when they don't apply. If you have got an ionic substance, that contains ions, and therefore you cannot talk about molecules or strong or weak intermolecular forces. You cannot talk about covalent bonds, and you cannot talk about delocalized electrons because they do not exist in an ionic substance. Likewise, a covalent substance consists of molecules, and therefore it's no good talking about ions, and it's no good talking about delocalized electrons because they do not exist in a covalent molecule. And lastly, metallic substances consist of ions which are positive and delocalized electrons. So again, it's no good talking about covalent bonds or intermolecular forces in a metal because if there are no molecules, there cannot be intermolecular forces because intermolecular forces are forces between molecules, and if there's no molecules, you can't have intermolecular forces. Right, okay. I hope that makes sense. This should be something where it's really easy to pick up lots of marks. And it might be that people just didn't revise them, but there's so many easy points here. Going through these then, there's two ways of answering this. We could start off with one property in turn and go through all the substances and move on to the next property, or you could pick a substance and go through all the properties for that substance. It's probably easier to do it property by property and deal with the substances at the same time. So, if we take melting point first. We have got calcium, which has got a high melting point. We should have said calcium is a metal and contains positive metal ions surrounded by a sea of delocalized electrons. So that is my statement. I now need to explain why this causes a high melting point. So I should say there are strong attractions or metallic bonds between the positive ions and negative electrons. Which require a lot of energy to break. So calcium has a high melting point. Okay, next. Chlorine has a low melting point. So we should say chlorine has weak intermolecular forces between covalent molecules, because we know chlorine as a halogen is diatomic, it goes around in pairs of Cl2s. And because we have these weak intermolecular forces between the molecules, they require very little energy to break. And because they require a small amount of energy to break, chlorine has a low melting point. Lastly, calcium chloride has a high melting point because calcium chloride is ionic and has lots of strong electrostatic attractions between the oppositely charged ions. I cannot use the word molecule or atom or particle because they are not correct. An ionic substance is made of ions. Because there are strong electrostatic attractions between the oppositely charged ions, they require a lot of energy to break. So, calcium chloride has a high melting point. I've only covered melting points. I haven't even touched the ability to conduct electricity yet, and yet I've already got 3 or 4 marks just from doing that. Right, next bit, ability to conduct electricity. Because calcium and chlorine have the same ability to conduct electricity when solid and when molten, that doesn't change when they change state, I don't need to write 2 separate points for each one. I could do if I wanted to, but I would be repeating myself. So, if we do conduct electricity, calcium conducts electricity well all of the time. Chlorine never conducts electricity well. Calcium chloride does not conduct when solid, but does when liquid. So again, same idea. If we put conducting electricity, first thing I would start with is calcium is a metal and contains delocalized electrons. Which can move. Moving electrons are an electric current. So calcium always conducts electricity. And again, I should refer back to what they said in the question. They specifically said when solid and when molten. So I should specify here. So calcium always conducts electricity when solid and when molten or melted. Okay. Chlorine is a covalent molecular substance. So does not contain delocalized electrons or ions. There are no charged particles. That statement is not true. There are charged particles in chlorine because chlorine contains protons and electrons. However, there are no charged particles which can move. That movement is the important bit. If the charged particles cannot move, then the substance cannot conduct electricity. So, there are no charged particles which can move in chlorine molecules. So, chlorine never conducts electricity. And again, referring back to what the question actually asked me, never conducts electricity when solid or when molten. Lastly, calcium chloride Calcium chloride is ionic. Again, linking back to the bonding and repeating it. And contains ions. Now this is where it gets a bit more complicated, because calcium chloride's conductivity changes from poor when solid to good when molten. So this time we can't sum it up in one point, we have to make two separate points. So we should say calcium chloride is ionic and contains ions. When solid, the positive and negative ions cannot move. That is the key point. I'm going to add a little bit more because it's a good idea too, but that's the key point, because, and rather than they, I'm going to write the ions are locked in place in an ionic lattice. And that is the bit where they're held in place by the strong electrostatic attractions or ionic bonds we talked about for the melting point. If the charges or the charged particles or the ions cannot move, so calcium chloride does not conduct when solid. When liquid or dissolved, calcium chloride does conduct electricity. And therefore, we should say, when molten, the ions break apart and can move, and therefore we've got the moving charged particles because the ions can move. Calcium chloride does conduct electricity. And again, I might not need to write this, but at the moment that sentence is unclear exactly what I'm talking about. So I'm going to say, because the ions can move, calcium chloride does conduct electricity when molten. And it's all, again, that thing of being precise, being specific, and making sure I really, really clearly answer what I've been asked. And for the people I teach, if you look through that answer, the word it does not appear in there a single time. The word they does not appear in there a single time. I have specified what it is, I am talking about every single time. So there's no confusion, and the examiner has to give me the marks. Question 9 is all about acids, which is topic 4. The first part is asking why dilute hydrochloric acid is a strong acid. This is one of those bits that's not helped by the fact that lower down the school we talk about strong and weak in the wrong way. A strong acid is an acid that completely dissociates or splits up in water. that is a non-reversible reaction. It just happens and they stay split up. And the words we need are either ionizes or dissociates or splits up would be acceptable. And the second part, for the second mark, is to say what this splits up into. So this ionizes or dissociates or splits up into hydrogen or H plus ions and chloride or Cl minus ions. You didn't actually need to mention the chloride or Cl minus, but it's a good idea. But the key point is that acids produce the hydrogen or H plus ion in water, and the strong acids completely split up, so there's no undissociated acid left. It's all hydrogen or H plus and whatever the negative ion is. For part 2, you've been told that 1 centimetre cubed of hydrochloric acid of pH 2 is made up or diluted into a volume of 10 centimetres cubed. We should remember that 1 pH unit is a factor of 10. So if I've gone from 1 centimetre cubed to 10 centimetres cubed, this has got 10 times less acidic, and therefore I have gone from pH 2 to pH 3. Because 1 pH unit is a 10 times difference in acidity, and if this has got less acidic, the pH is higher, so it's pH 3. Part B, you were asked to write an ionic equation for this reaction. They gave you the balance symbol equation, and we should have gone through and just translated this into an ionic equation. Remembering the rules for an ionic equation, any ionic substance that is dissolved in water we write out as the ions. Anything else stays as the formula. So in this case, the hydrochloric acid is dissolved in water, so this will split up. The magnesium chloride is dissolved in water, so this will split up. But the magnesium oxide is a solid, so doesn't split up. And the water is a covalent liquid and does not split up. So the ions involved here are the magnesium oxide remaining as a solid and 2 lots of H plus and 2 lots of Cl minus reacting to produce the Mg2 plus ion and 2 lots of Cl minus and water. But this is not quite finished, because in an ionic equation the last step is to remove any spectator ions that are the same on both sides. The only thing that is a spectator ion here is the chlorides, so I should remove my 2 lots of Cl minus, and therefore if I neaten this up slightly, my final answer is magnesium oxide and 2 lots of H plus react to give magnesium 2 plus and water. Part C, this one there was many interesting answers to. You were asked first off for something that can be used to measure pH, but also the name of a piece of equipment, and therefore this has to be something that you can actually physically use, and it's an alternative piece of equipment which cannot be used as universal indicator paper. So therefore, just repeating use universal indicator paper did not get you the marks, was said to be an alternative piece of equipment. The easiest and best answer here is a pH meter or a pH probe. Right, part 2. You are asked to state and explain how the pH changes as the magnesium hydroxide is added to the dilute hydrochloric acid. So, first bit, the state. There's 4 marks here. The state is the easy bit. What actually happens to the pH? Well, the acid is being neutralised, so the pH is increasing because the solution is getting closer to neutral. So the first thing we would say is the pH increases. But the pH doesn't increase all the way. The pH increases until the pH reaches 7. The reason why the pH does not keep going is because if we look at the equation, magnesium hydroxide powder is being used, and therefore this is a solid, and we're going to stop once the magnesium hydroxide is just in excess. So we're adding just enough solid for all the acid to react and not continuing to go up into more and more alkali pH above 7. Right, the reason why this happens, the explain bit is trickier. What happens is the hydrogen or H plus ions react with the magnesium hydroxide. And because pH is the concentration of hydrogen ions, as the concentration of hydrogen ions decreases, the solution becomes less acidic and the pH is increasing. So we should have said the H plus or hydrogen ions react with the magnesium hydroxide. That's the first part of my explanation. And therefore the concentration of hydrogen ions decreases, which means the pH has increased. You didn't have to use those exact words. We could have said all of the hydrogen ions have reacted. Question 10 is mostly about equilibrium, which is topic 5 and 6. For the first part, you are asked what the effect of adding an ion catalyst is on the rate of attainment of equilibrium and equilibrium yield. First off, we should remember that catalysts increase the rate of a reaction, and therefore my answer must be either A or D, because catalysts make reactions faster and therefore the rate must increase. Hopefully we also remembered that a catalyst affects the rate of the forwards and backwards reaction the same, and therefore the yield of ammonia does not change. So my answer must be answer D. Question 2, which of these statements is correct when the reaction reaches equilibrium? So at equilibrium, the forwards and backwards reactions are happening at the same speed. So the reaction doesn't stop, so it's not D. The reverse reaction has been happening all the time, so it's not A. Which leaves B and C. At equilibrium, the amounts of the chemicals do not have to be the same. All that's required is that they are not changing. So the answer must be answer C. Part 3 is about equilibrium again, and has asked you to explain, i.e. give a reason for, the effect a pressure higher than 200 atmospheres, so a higher pressure, would have on the rate of attainment of equilibrium and on the equilibrium yield. There's 4 marks for this. Normally, it would be 2 marks for each point, one for the answer and one for the explanation. However, because rates of reaction is topic 7 and therefore not covered in this paper, most of the marks are for the equilibrium yield and the effect on the equilibrium position. So, the first thing we should say is that the rate of attainment of equilibrium would increase. And again, if they have asked me in the question about a specific phrase, that is the phrase I should use in my answer. I shouldn't just say the rate increases, I should say the rate of attainment of equilibrium, because that is what they've asked me in the question. So the rate of attainment of equilibrium would increase because there would be more frequent successful collisions between the particles. That bit doesn't actually get you any marks, but is still an important phrase we should know. Anytime you are asked about increases in rate, or in fact anything to do with the rate of a reaction, putting in the phrase frequency of successful collisions almost guarantees you a mark. It doesn't in this case because topic 7 isn't in this paper, but it's still good practice. Right, the equilibrium yield. We need to look at the equation and we can see I've got 1 mole of nitrogen, 3 moles of hydrogen. So on the left side, I've got 4 moles of gas in total. On the right side, I have 2 moles of ammonia. And therefore, if I increase the pressure, the system will try and decrease the pressure, and therefore will do the forwards reaction because that makes less gas molecules and therefore fewer moles of gas. And that is essentially the answer here. I've got my first mark for the rate of attainment of equilibrium increases. The next point is to say the equilibrium yield of ammonia, because in an equilibrium I can reform my products and therefore could be talking about the equilibrium yield of nitrogen and hydrogen. The equilibrium yield of ammonia will increase because there are fewer moles of gas on the right side of the equation. So the forward reaction is favoured. Because the system tries to decrease the pressure. Question B. Ammonium sulfate and ammonium nitrate are both used as fertilisers, as they both contain nitrogen. One other reason for using solid ammonium sulfate and solid ammonium nitrate as nitrogenous fertilisers. The best answer here is that ammonium salts are always soluble, and therefore both ammonium sulfate and ammonium nitrate are soluble, and that's really all you need for the mark, but it'd be better to add the explanation. So the ions can be absorbed through plant roots. Okay, part 2. Ammonium nitrate can be made by the reaction of ammonia with nitric acid. We should know the formulas of ammonia and nitric acid, and you got 1 mark just for those. Ammonia is NH3 and nitric acid is HNO3. Again, if you forgot the formula of nitric acid, you could always work it out. We know the nitrate ion is NO3 1-. We know all acids contain hydrogen, and the H plus and NO3-, the plus and minus cancel out, so nitric acid is HNO3. The second mark was for the formula of ammonium nitrate. Again, we should know the ammonium ion is NH4 1+. The nitrate ion is NO3 1-. And again, the plus and minus cancel out. So ammonium nitrate is NH4 NO3. You weren't asked for state symbols for this, but if you wanted to, you could have put them in. Ammonia is a gas. Nitric acid will be aqueous and dissolved in water. Ammonium nitrate is soluble, so it will be aqueous and dissolved in water. Last question asks for 1 similarity and 1 difference between the industrial production of ammonium sulfate and the lab preparation of ammonium sulfate. This one was another one that people made much more complicated than it needed to be. The main similarity between these two is that to make the sulfate, we use sulfuric acid. So we could have said both processes use sulfuric acid. You could also have said they use the same reactants or the same chemicals. Differences. The main difference is that industrial production is on a much larger scale than lab production. And again, I'm making that comparison. I'm not just saying industrial production is larger. I'm saying industrial production is larger than lab production. We could also have said that industrial production is a continuous process, i.e. it does not stop. And lab production is a batch process. In a lab, you make some ammonium sulfate, you tidy up the equipment. If you want to make more, you then start again from scratch. Industrial production uses massive reacting vessels that you continuously pump chemicals into one end and extract the product out the other.